Managing your app data using Signals is quickly becoming the default solution in web development. Both new players in the framework space and big established names in the industry are betting on this architecture. So what's all this fuss about, and why should you even care? After all, Signals are not a new concept in software development, but all of a sudden you are seeing them everywhere these days. Let's start with a basic app example and work our way up to a signal-based implementation to get a better understanding of the problems we are solving. In a JavaScript file, I'm defining two plain JS values. To display them in the DOM, I'll create a new document element and update its inner HTML value accordingly. Then, I'm also adding a button with a click event handler, which simply increases the value of the counter by 1. When the user clicks on the button, the counter value is updated, but the double value and the container HTML will stay the same. Of course, this is expected since our code is not reactive. So, for my app to work as expected, I need to jump into the click listener and make the updates in an imperative manner. If you are familiar with the modern web development standards, you probably know we can do better than this by pairing a declarative style with reactivity. Reactivity implies that whenever the state changes, associated values and DOM elements should be updated as well. In other words, updates to the double value and the container HTML should also be triggered by some mechanism running in the background. To achieve this, we'll start by upgrading the counter value from a value to a signal. This will turn the counter into a construct that can hold a value while also maintaining a list of dependencies. Associated computed signals and effects will silently register themselves in the dependency array, and whenever the value inside the signal will be updated, these dependencies will rerun. Don't worry, we'll look at all these implementation details in a second. Following this logic, the double value will become a computed construct, which doubles the counter signal value, and the container's HTML will be updated in a side effect. With a bit of refactoring, the final implementation will look like this. When the button is clicked, we'll simply update the counter, and then everything else will be updated and synced under the hood. For the implementation details, let's jump into a signal.js file where we'll create a class called signal. This will have two private fields, the actual value and the list of entities depending on this signal. We'll initialize these values in the constructor, and now we can get to something a bit more interesting. I mentioned a bit earlier that dependencies will silently subscribe to our signal. In order to do this, we'll need a special context which keeps track of the effect or computed value being executed at any given time. In proper implementations, this context will be a little bit more complex, but for our naive implementation, it is enough to keep track of the active running function via a global variable. I'm also defining a simple run and extract dependencies function, which receives the effect or computed function as an argument, will mark the task as actively running, and then will simply execute it. Back to the signal implementation, whenever the value is accessed, we can check if this is a run triggered by our extract dependencies function, and if that's the case, we'll update the dependencies list. Then I'm simply returning the internal value. In the setter, we'll make sure the new value is updated internally, we'll run through the dependency set and call an update function to refresh each dependency. Next, the computed class has three private fields, a cached value, the function associated with this construct, and an isStale flag we'll use to ensure the function is re-executed only when needed. Note that in the constructor, we are calling the run and extract dependencies function with the object sent as a reference. Again, this will execute the computed function, and whenever a signal value is accessed, this computed instance will be added in the signal's dependencies array. In the getter, we'll make sure to recompute the value whenever the construct is stale, and, of course, the construct is becoming stale whenever observed signals are updated. Finally, the effect class follows the same ideas we already went through. The dependencies are executed, and whenever the associated signals change, the effect function is rerun. Of course, in the real world, a proper signal implementation will be more complex, with fail-safes and better dependency management, but these few lines should give you an idea about the core concepts. Signals allow UI developers to perform DOM updates in a very targeted reactive manner, which turns out to be a way more efficient strategy than the diffing solution some other frameworks like React are employing when tracking DOM updates. In other words, while React compares virtual DOM snapshots and reevaluates entire components when state is changing, a signal-based architecture will simply compare the signal values and will run the associated effects if needed. This efficiency is what makes some of the established frameworks rethink their reactivity models and adapt a signal-based architecture moving forward. Signals are not the only popular pattern used to make observers react based on changes in monitored subjects. The observer or the pub sub pattern are also commonly used in web development. This video is part of a short explanation series where I'm reviewing dev concepts such as these ones, so please click the like and subscribe buttons if you are interested in more similar content. Until next time, thank you for watching.